Hello, I'm basically making a Sekiro clone, a third-person Souls-like with parry-focused combat. In my last devlog, I showed off some great progress on the underlying systems behind the enemies in my game, which will allow me to efficiently create engaging encounters. I introduced different enemy types, refactored code to make everything modular and configurable, and added a patrolling mechanic. At the end of the devlog, I said this: after a few more fixes and improvements here and there, the demo was ready. A few more fixes and improvements. This passing remark was a massive understatement. I was testing the new level on my Steam Deck and I would struggle to get 60 FPS, going as low as an average of 8 frames per second in this one area. I would also get really noticeable lag spikes. It wasn't great. Sekiro gets around 50 FPS, fluctuating from 40 to 60 on medium settings, but it has a fair amount of 3D models, textures and systems in place. Compared to my barren, low poly prototype, I really needed to improve on its performance. With that in mind, I spent 3 days scrambling to optimize my game for the release of the demo, rushing to improve its performance since the semester of university had already started and I didn't want to fall behind on schoolwork. I didn't include this in the previous devlog because the video was already getting pretty long and I just didn't have the time to add it in. So here's how I optimized my game. I've done some optimizations like occlusion culling and removing nodes when not in use, but that's clearly not enough. The first thing I did was to look around for more avenues to explore. I've already gone through the optimizations recommended in the Godot docs, but what really guided me was this video by Blargis. They covered several ways to optimize their game, and so I took a few of those ideas for myself. Godot's built-in profiler isn't terrible, but it isn't the best either. It's really good at finding which one of your scripts are causing trouble, but this process metric provides absolutely no information. I read about using C++ profilers from the docs when I initially tried optimizing my game, but it felt too intimidating at the time. But now I really wanted to know what was actually happening during this process step. To do so, I had to compile Godot to include the debug symbols, which was actually pretty simple as it was well documented. After that, I downloaded Hotspot, a C++ profiler for Linux, and I was ready to go. This is a flame graph. The colors don't really mean anything. The height just indicates the call stack. So in this top-down view, it tells you that a method calls the method above it. What's really important is the width of these cells. The wider it is, the more processing time relative to the others it does. As you can see here, this process animation method is huge. I initially thought it had something to do with me constantly setting values in the animation tree within the process function, so I set up a guard clause to return early if the values don't need to change, reducing the amount of times the animation tree is accessed. But putting these guards within all my animation scripts did basically nothing to improve performance. The real reason why the process animation method is so large is due to the actual calculations that the animation tree does. This method performs calls to blend calc total weight, blend process, and blend pre-process. My animation trees use a lot of these blend nodes, and so I think the calculations that blends the animations together are just computationally intensive. This ended up being the reason why I was getting 8 FPS in this one area. At this point, there are 23 active enemies. Most of them we can't even see, but the animation blending is still being calculated even though they're just idling. To fix this, we'll just turn off the animations if the enemies are off the screen. This is what Blargis did in his video, which he got from a Miz video. Basically use a visibility on-screen notifier node to activate or deactivate the animation tree. It was a really simple fix, but this did cause a problem. I use root motion for my enemies, and so the movement in the animation is used to move the enemy itself. But if I turn animations off when I don't look at them, they stop moving. It's like the opposite of Weeping Angels or that one video of the stalking cat. This also affected the patrolling enemies, which would act like lazy guards who only patrol when you're looking at them. Luckily for me, I've built the enemy system so that I can easily switch between root motion and programmatic movement. The velocity of the enemies will be set directly if you can't see them anymore, but since I sometimes choose root motion or programmatic movement in different situations, I save the previous locomotion method and restore that when the enemy comes back into frame. By the way, for anyone else looking to do this, make sure you set animations to be off by default. The notifier only notifies as nodes come into and out of the screen, so they should initially be off and only animate when you see them. Disabling the animations reduces the unnecessary computations of the blend trees when we don't actually see the models. As a result, this process animation method became 55% smaller. I'm not sure if that's even remotely accurate in terms of performance gains, but the colourful box got less wide, so that's a win in my book. It's still relatively large though, so if anyone watching has any more ideas on optimizing the animations, I'll be very grateful. Another thing I tackled is this column here, which is the navigation agent code. It's probably not surprising that pathfinding is computationally extensive. Each enemy has to calculate a path to the player through the navigation mesh each frame. To optimize this, I used Blargis' approach and reduced the pathfinding calculations to occur once every 20 frames instead of every single frame. I also made sure to randomly initialize what frame they start at so that the enemies don't all update at the same time. These changes made the navigation blocks super thin, which was great to see. The enemies do rotate towards the player based on this navigation system, so now they do rotate in a noticeably laggy way and are a bit delayed, but I'll fix this some other time. Back to the flame graph. This column here looks like it's for loading in resources. I tried to optimize this by creating a global dictionary for resources. Beforehand, I duplicate resources for the colors of an enemy's parry particles and shield. The same type of enemy should have the same color for their parry particles and shield, so they should just use a shared resource instead of each enemy having their own separate one. Initially, this global resource dictionary is empty. When the first enemy checks for the resource and finds nothing, they'll create it and add it to the global dictionary for other enemies to use. This approach basically provides a simple singleton with lazy initialization. This didn't really affect the width of the column. I think this part deals with loading resources initially. These parry and shield resources are only a small amount compared to the lots of other resources that gets used within the game. But minimizing the amount of resources is still good practice, so I'm happy with my little solution either way. Other than the animation processes, there isn't really anything that noticeable to optimize now. I'm not too sure what to make of this left section. I think it's for the visuals and rendering side of things, but feel free to correct me on that. These look like NVIDIA binaries, but the debug symbols are missing, so there's just question marks there. This block is pretty wide, but it looks like it's for occlusion culling, and that's been a massive help in performance, so I'm not sure whether I should be messing with that. And this section just deals with managing race conditions, which seems like it's out of my control anyway. I did notice that the amount of calls for the behavior tree nodes in the built-in profiler could be improved, so I disabled the behavior tree when an enemy is idle and after an enemy dies. This just squeezes a bit more performance out of the game. Those were pretty much the optimizations I did for the overall FPS in terms of processors. The next biggest problem I had were these massive lag spikes. I knew what the issue was though because I implemented the thing that caused them. You can even see the massive spike in processing time in the built-in profiler. It points to my code which adds and removes enemies from the level. I will say that another gripe I have with the profiler is its behavior in displaying the graph. It's like the observable time frame changes or something, which is really odd. If I pause the profiler, there's a good chance that I didn't time it correctly and the spike just doesn't show up. Anyways, I read from the documentation that removing nodes from the scene could improve performance. So I was removing enemies based on sections, and yeah, this ended up being really great. See here, enemies from one section are being removed while enemies from another are added back in. Each enemy is made up of a bunch of nodes, so I end up adding and removing a lot of nodes at the same time, resulting in these lag spikes. This occurs when entering or leaving the colliders of the sections. I tried setting them up so that you don't leave one section and enter another section at the same time, but even by themselves, there's still a lot of nodes being added or removed. This does seem to be a problem with Godot, as I found a few issues relating to adding and removing a bunch of nodes, resulting in lag. Since the main problem was a massive lag spike when performing these changes on so many nodes in the same tick, I just staggered them. If the player leaves an enemy section, each enemy will be removed one by one with a 0.2 second delay between them. If the player enters an enemy section, enemies will be added one by one with a 0.2 second delay as well. I have to be a bit more careful where I make sections start so that the player doesn't see enemies just appear out of nowhere in front of them. But this removes the massive lag spike during a particular frame. In terms of graphics, I set my sights on these character models. This was pointed out by Berific ages ago. They mentioned that these models have 55,000 triangles. That's just way too detailed. They do look really good. I love how smooth and clean they are, but I think I'll end up going with a low poly art style anyway. So for now, I just did a good old fashioned decimate on the model, which brought it all the way down to 2,766 triangles. In the future, I'll be more mindful of the polygon count of the models that I use. The second graphics optimization that I did was to use static lighting. Again, Godot's documentation was really great and the process was simple. I set the import settings of my levels to use static light maps, made the omni-lights on the checkpoints and light posts to use static lighting, added a light map GI node to my scene, and baked the light maps. I actually tried doing this when I was initially doing optimizations, but that was before Godot 4.2, and when I tried to bake the light maps, the engine would just crash, so I'm very glad it works now. The only bummer was not being able to include the directional light, which creates most of the shadows in the scene. Right now, if I were to bake the directional light, it would bake the shadows of the level, which is great, but it wouldn't allow for shadows of the player, a dynamic object. There are a couple pull requests for Godot that work towards improved configurations, so I'm excited for those updates. There's still a lot for me to learn about lighting, both optimizations and just using them effectively from a design point of view, so any comments are much appreciated. I also came across an absolutely embarrassing memory leak. Every time the player dies, the amount of objects just skyrockets. Funnily enough, this problem stems in part from my optimization of adding and removing enemies in the sections. Just to reiterate, these sections would remove their enemies when the player is not in the section. When the player dies, I just deleted the parent nodes containing these sections and assumed all the enemies would also get deleted. But since the enemies are removed from their sections, they still exist. They're just no longer children of the sections. So when a section is freed, those removed enemies don't get deleted and just stick around. The system is supposed to work by deleting all of the enemies and then instantiating them again. But most of the enemies don't actually get deleted, so the amount of objects increases after the player respawns. To fix this, I explicitly made sure that a section frees all the enemies it manages, instead of relying from a call from an upstream node that doesn't take into account removed nodes. There's still like a marginal increase in the baseline after respawning, but it's mostly fixed for now. I'm tempted to hunt down what's not being properly deleted, but I'm gonna force myself to move on. Although after looking at the spikes on these graphs, I feel like I could be a bit more efficient in how I handle resetting the enemies, but that's for another day. The next one isn't even close to an optimization, but I want to share it anyway. I have this logic with the player model that would extend their legs as they reach the ground after jumping. This was to make the recovery phase of the animation more natural. I still need to make the player bend their legs as they land on the ground, but I'm procrastinating on that for now. I used the raycast pointing straight down to detect when they should extend their legs. This worked for the most part, but it didn't actually follow the player's trajectory, it always points down. So if the player would fall past a ledge, but be close to landing on it, the raycast would assume the player was about to land and the model's legs would extend. This made it look very weird. Notice how the player just starts standing still in the middle of the air. What I needed to do was to align the raycast to the player's velocity so that it doesn't clip the edge, and instead to only hit the ground when the player is actually going to land. This was unbelievably confusing. I tried to figure this out myself, looking into quaternions and transforms, but I just couldn't get it to work. The fact that I still don't know how quaternions or transforms work probably didn't help, but it sounded like such a simple thing to do. Just align the raycast to the velocity vector. I somehow found this snippet from Kids Can Code to align a body to a surface. I'm still baffled that I found the solution using this, since this seems completely unrelated. It talked about aligning the transform's y-axis to the normal vector. Praise to the Godot plushie that I managed to connect that with being able to align the raycast's y-axis to the player's velocity vector. At the end of the day, this bit of code really is elegant, and it actually ended up being a really simple thing to do. Just that I didn't know how to use transforms properly to get the solution on my own. With that, the player extends their legs when they're actually about to land on the ground. After all those optimizations, I get a really smooth 60 FPS on the Steam Deck, which I was very happy with. We'll see how it goes, trying to keep it to the 60 FPS when adding in more content to the game, but that's all for now. If you want to give the game a try, you can play the demo in the link in the description below. I'll see you in the next devlog where I'll be implementing the boss fight mechanics.